When most of us picture advanced mathematics, we imagine incredibly complex number crunching. We think of people standing in front of chalkboards, executing brute force calculations faster and more accurately than the rest of us. The Fields Medal-winning mathematician Terence Tao points out a distinct flaw in this view. Throughout history, the greatest breakthroughs in math almost never came from calculating faster. They came from someone stepping back and looking at the problem from an entirely new perspective. Humans possess a specific cognitive superpower, conceptual compression. Instead of checking millions of messy individual cases, human brains naturally hunt for a hidden structure, a single elegant pattern that collapses all that complexity down into a simple rule. True mathematical genius requires reframing reality to ask a completely different question. Look at the 19th century mathematician Bernhard Riemann. He decided to abandon the traditional rules of flat Euclidean planes altogether. He imagined entire new worlds of curved, non-Euclidean spaces. Non-Euclidean geometry means studying shapes on curved surfaces, like spheres, rather than flat pieces of paper. Take a look at this diagram showing a flat two-dimensional grid warping into a complex, curved three-dimensional shape. Riemann's radical shift in geometric rules directly provided the mathematical foundation for Albert Einstein's theory of general relativity decades later. We see the exact same process in modern times. When Andrew Wiles finally proved Fermat's last theorem, he didn't attack the equation through brute force. He translated the entire problem into a completely different field of math dealing with elliptic curves. Elliptic curves are specific types of cubic equations that plot complex, donut-like shapes. Human mathematicians act as cartographers of abstraction. We invent the conceptual worlds before we map them. There is a hard biological limit to this kind of insight. Human brains evolved to navigate physical environments in 3 dimensions. We are exceptional at spotting simple symmetries and avoiding predators in the physical world. But modern physics operates in places our biology never prepared us for. The math underlying our universe now relies on unvisualizable 50-dimensional manifolds and infinite Hilbert spaces. A Hilbert space is simply an infinite-dimensional algebraic concept used in quantum mechanics to map every possible state a system can exist in. Once math enters these extreme high-dimensional territories, our ability to visualize objects completely fails. Natural human intuition becomes dangerously unreliable. To accurately map the unknown territories of quantum mechanics and string theory, humanity needs a navigational tool completely detached from our sensory evolution. This is the domain of artificial intelligence. It functions as an alien cognitive species. Where human mathematicians rely on intuitive insight, AI approaches the exact same problems through high-dimensional search. Imagine exploring an unknown continent. A human climbs to the top of the highest mountain to deduce which way the rivers most flow. An AI operates like a cosmic survey drone, simultaneously walking every single square millimeter of the terrain. This animated map shows a high-dimensional data cluster being systematically scanned. Neural networks process unvisualizable mathematics by treating them as massive data structures within a latent space. A latent space is a compressed, multidimensional map where an AI stores and relates different concepts based on statistical patterns. When the machine flags a massive geometric anomaly or statistical regularity across billions of combinations, the loop completes. Human mathematicians examine that raw output to extract the actual conceptual meaning. The machine does not understand the mathematics. It acts as an absolute, tireless explorer, returning from the dark with the raw materials human minds need to build with. This brings us to a fascinating philosophical boundary. Can an AI actually decide to abandon old rules and invent entirely new mathematics, the way Riemann did? Current AI systems are confined to fixed formal systems. They manipulate symbols based on pre-programmed logic. And axioms. Axioms are the starting rules in mathematics that are accepted as true without requiring any proof. The machine cannot rebel against its own parameters. Because of this strict confinement, there is a persistent fear that AI will always remain a mere calculator, incapable of triggering a true conceptual revolution. Judging a machine purely by its ability to replicate human creativity completely misses its actual evolutionary purpose in science. Terence Tao proposes a brilliant metaphor for this dynamic. AI is a mathematical telescope. A telescope does not replace the astronomer looking through it. It expands the observable universe of mathematics. The machine reveals massive structural relationships across datasets so large our biological minds could never perceive them alone. We are stepping into a continuous, hybrid dialogue. Human intuition dictates the conceptual direction, and machine computation scales that intuition into infinity. For thousands of years, mapping the abstract world was a uniquely human endeavor. The future of discovery requires the unprecedented merging of two completely distinct forms of intelligence, exploring the fabric of reality together.